Good morning everyone. Myself Devika, working as assistant professor in the Department of Electrical and Electronics Engineering at Sri Muthukumaran Institute of Technology. In this presentation, we have discussed the subject on MR3452 Control Systems Engineering for 2021 regulations. In this presentation, we have learned the topic Stability of Control System, which is the Unit 4 in Control Systems Engineering. Then overview of stability of control systems, introduction, understanding stability, habits and Brown stability criteria, summary and final thoughts. Then understanding system stability. Stability refers to whether a system maintains its equilibrium or diverges over time. There are three distinct categories of stability. One is stable system, unstable system, marginally stable system. In stable system, the system returns to equilibrium after a disturbance. In unstable system, the system moves away from equilibrium when disturbed. In marginally stable system, the system neither settles back nor diverges, remaining on the edge of stability. Then types of systems. Stable system. A system is considered stable if every bounded input results in a bounded output, ensuring predictable behavior. Then unstable system. When a system produces an output that grows without limiting a response to a bounded input, it is classified as unstable. Then marginally stable system. This type of system, when subjected to an infinitely large impulse input, generates an unbounded output that does not settle back to zero, indicating a delicate balance between stability and instability. Then categories of control system stability. BIBO stability, bounded input, bounded output. It ensures that when the input remains within limits, the output also stays confined within a finite range. Second one, asymptotic stability, that means zero stability, and the system's output will eventually settle to zero if the input is zero. Then absolute stability, the system remains stable for every possible value of its parameters as long as the input is bounded. Then relative stability, it measures how far the system is from becoming unstable, it providing insight into its robustness. Then conditional stability, the system is stable only within specific ranges of one or more parameters, outside of which instability may occur. Then Routh-Hurwitz stability test. So the Routh-Hurwitz method provides a systematic way to verify if every root of a polynomial lies in the left half of the complex plane, meaning all have negative real parts. Then to assess a system stability, start by scattering its characteristic equations. Then a fundamental requirement for stability is that every coefficient in the polynomial must be strictly positive. If any coefficient is 0 or negative, it indicates the system cannot be stable. And having all positive coefficients does not guarantee system stability. Even with positive coefficients, the system's root might be located in the right half of the S-plane or on the imaginary axis. So, the Hurwitz and Routh developed a method to determine sufficient conditions for system stability. So, it involves arranging the characteristic equations coefficients into a structured format known as the Routh array. Then Routh-Hurwitz stability criteria. For a system to be stable, all coefficient of its characteristic equation must be located on the left side of the S-plane. This condition is necessary but alone does not guarantee the closed loop system stability, or that all roots of the characteristic equation lie on the left half of the S-plane. To address this, the Routh table is introduced as a method to access stability. The characteristic equation for the n-order continuous system is expressed as below. A power an s power n plus a n minus 1 s power n minus 1 is etc. a1 s plus a0 is equal to 0. the characteristic equations for this Routh-Hurwitz stability criterion. Stability is evaluated using the Routh table. This is the table which is constructed based on the coefficient of the characteristic equations. For example, the characteristic equation is highest coefficient is odd number, means first row is odd number of coefficients, second row is even number of coefficients, then odd number, even number. Likewise, the characteristic equation of higher coefficient is even number, means that means 4 or 6, means the first row of Routh table is even number, the second row of Routh table is odd number, then even number of coefficients, then odd number of coefficients. Likewise, so here the coefficients of a power n minus 1 till a naught represent the terms of the characteristic equations. For example, we have to find b1 is equal to a n minus cross multiplication of first row second row, a n minus 1 2 into a n minus 2 minus a n into a n minus 3 divided by a n minus 1. Likewise, b2 a n minus 1 a n minus 4 minus a n minus 5 divided by a n minus 1. Likewise, c1 c2 c3 we have to find for this for like this. Then case 1, standard Routh-Array analysis. Being by forming the Routh-Array, and then it observes the changes in sign within the first column to determine how many roots lie in the right half of the S-plane, which helps assess system stability. Then the first column shows no sign changes. It indicates all roots are located in the left half of S-plane, so the system is stable. Conversely, if sign changes appear in the first column, the system is unstable. So the count of these changes corresponds to the number of roots in the right half of the S-plane, while the remaining roots reside in the left half of the S-plane. This one is first case. Then case 2, entire row of zeros. The presence of row filled entirely with zero signals that the characteristic equation includes on even polynomial as a factor. So an even polynomial is defined by having only even powers of the variable s including 0. This even polynomial factor is often referred to as the auxiliary polynomial. So the coefficient of this auxiliary polynomial corresponds to the elements found in the row immediately above the 0 row within the array. The roots of an even polynomial appear in pairs, with each pair consisting of values equal in magnitude but opposite in sign. Consequently, these roots may be purely imaginary, purely real, or complex numbers. So identify the auxiliary polynomial denoted as a of s. So compute the derivative of a of s with respect to s, represented as d one-time differentiation with respect to s. So substitute the 0 rows in the array with the coefficients derived from dA divided by ds equal to 0. So proceed to complete the construction of the array, examining the first column of the array. If any sign changes occurs, the system is unstable. The count of these sign changes correspond to the number of roots located in the right half of the S-plane. The auxiliary polynomial helps estimate how many roots lie on the imaginary axis, while the remaining roots are positioned in the left half of the S-plane. This is a case 2. Then case 2, a 0 only in the first column. There are two methods in case 2. Stability via Epinson method, stability via reverse coefficients. Drawbacks of the Hurwitz criterion. Calculating large determinants for higher order systems is extremely labor intensive and time consuming. Then this method does not specify the precise count of poles located in the right half of the complex plane. Assessing marginally stable through determinant evaluation becomes increasingly challenging when using this approach. Conclusion: this presentation has provided an introduction to the fundamental principle of stability along with an overview of these key concepts. We explored how Routh-Hurwitz criterion serves as a practical tool to determine whether a system maintains stability. In real-world applications, ensuring relative stability is often the preferred approach to system design and analysis. Thank you.